questions from the past day? Yeah.
I have a question.
Uh-huh.
How come, in terms of polarization, why are smaller orbitals less polarizable than big orbitals?
Big versus small orbitals? Okay, it's, when we think about polarization, you know, one of the examples of polarization that came up was the dispersion forces. And so if we look at the boiling points of helium versus xenon. Helium and xenon both, over time, are nonpolar. You know, they have a very symmetric electron cloud. And so if we were to average this over time, and we look at the electron density distribution, it's pretty much symmetric here, here. The same thing with xenon. It's pretty much symmetric here. But in one instant of time, we could get an instantaneous dipole, right? This is all that instantaneous induced dipole. Well, think of the polarizability as being the induced dipole part. You know, and so, for example, here, helium has how many electrons? 2. And so if both of the electrons were to be on the left side of this, then we have an instantaneous dipole, delta minus here, delta plus here. And what that's going to do is this adjacent helium is going to see this delta plus, and that means the electrons in the adjacent helium are going to be pulled towards the left side by this one. And so we'll end up with a delta minus here. And this delta minus, delta plus attraction, that's our dispersion attraction there, or London attraction. Now, how many electrons does xenon have? 54 electrons. And so here, if we have 54 electrons total, I'm not talking about valence electrons, but let's say a lot of those electrons, maybe not all 54, because if all 54 were on the left side, it'd be quite a tremendous dipole. But let's say there are a bunch of extra electrons on the left side, and then we can generate much bigger delta pluses, much bigger delta minuses than in helium. And so what that's going to do is it's going to pull electrons. Now, pulling electrons over to it, inducing a dipole moment in the adjacent xenon depends on how tightly the electrons are held. Are the electrons going to be at least these outer electrons, are these outer electrons going to be held tightly to the nucleus? No, because it's a gigantic orbital. And so the electrons are kind of far out satellites. And so this is going to be easily polarizable. That is, the electrons will be pulled over here. All right, the other thing is, if we look at the instantaneous dipole, which one is it going to be easier to form an instantaneous dipole? When you have 2 electrons or when you have 54 electrons? 54, and so this is another indication of polarizability. Xenon is very soft, it's very polarizable. You can distort the electron cloud easily because it's got a lot of electrons, and those electrons aren't tightly held, whereas helium, those electrons are very tightly held. And it's hard to distort the electron cloud because there's not much space, there's not much room to move. Does that make sense?
Yeah.
And so that's and so helium would be considered more hard, less polarizable, although there's no electrons to donate. Usually when we talk about hard, we're looking at, bonding things. We'll talk more about it later. So which one will have a higher boiling point? Helium or xenon? Xenon has a much higher boiling point. A higher boiling point means a higher temperature is required to break that attraction. And in fact, helium's boiling point is 4 Kelvin, extremely low. It means these attractions are extremely weak. Whereas xenon, it's a lot easier to liquefy that or boil. All right, are there other questions to cover?
The electron configuration for chromium and copper,
Mm-hmm.
like what are the exceptions for those two?
Chromium and copper, you're talking about neutral chromium? Neutral chromium,
3+.
well, let's look at just chromium. If we look at chromium, we got the argon core, and then the next orbital would be the 4s. And so we'd say 4s, 3d, 1, 2, 3, 4. But yeah, this is the exception. The exception is this S gets promoted to the D, and we end up with this. Argon, 4s1, 3d, 3d5.
So that means chromium has 1 valence.
Yeah. Chromium would have 1 valence electron, the way we defined it, and that would be the, yeah, it would be this one, here. The outermost. Now, the half-filled shells, half-filled subcells, I should say, or sublevels are somewhat stable. So this is why this happened. But not terribly stable, so that when an oxidizer comes along and takes electrons, which electrons would be removed first? The 4s. And so an oxidizer comes, and then we get chromium plus 1. Now, one of the things about core electrons is core electrons are harder to oxidize, but these particular inner shell electrons aren't so hard to oxidize. Why? Because it's not a fill. You know, filled sublevels have an additional stability that's hard to break. And so in this case, if we remove another electron, we get chromium plus 2. And if we remove another electron, we get chromium plus 3. And so chromium plus 2 would be 3d4. Chromium plus 3 would be 3d3. Argon 3d3. Does that answer your question, Olivia?
So then it has 3 valence electrons for sure?
The reason why, and I got some questions about valence. You know, what exactly are valence? There are different ways to define. It's the same thing as electrolyte. You know, there are multiple definitions of what an electrolyte is. And so some people will define valence slightly different than I define valence. You know? In fact, I better make this clear because some people pointed out that in Chem 1A last semester, they learned that valence could include these. The reason I don't like to include the D's is because when you write the Lewis symbol, I want to write the Lewis symbol for chromium 3+. And so if I write the Lewis symbol for chromium 3+, how many valence electrons should I include in that symbol? Well, some people might say, well, there are 3. And so I better put 3 dots in here, like that. And then it looks like chromium can form how many bonds? Looks like chromium can form 3 bonds. You know, fluorine comes in here, bonds. Remember this kind of stuff? Another fluorine comes in here and bonds. Like this. Another fluorine comes in here and bonds. So 3 bonds, right? 3 bonds. And then it's less than an octet, and so we need to get something else in there. Does the octet concept hold for chromium? No. In fact, did you know that in these complexes, and this is something we're going to get to near the end of chapter 24. So I wasn't planning on talking about it now. I was going to talk about it later, but let me talk about it now. The d orbitals do not participate in the bonding in these complexes. And so I could have a bunch of d electrons in there. Those do not impact the bonds. Because the d orbitals are what in MO theory we call, in MO theory you had the bonding MOs and the anti-bonding MOs. Did you know there's another set of MOs? Do you know? The other set of MOs is called the non-bonding MOs. The non-bonding MOs are essentially just atomic orbitals. And so these Ds are actually non-bonders. They don't participate in the bonding. Usually the valence electrons got to participate in the bonding. And so what was that I had yesterday? Cobalt? Yes. If you have cobalt 3 plus, what was that? That was argon 3D 7? 3D6? Well, we're going to learn a simple way to do this when we come back to chapter 24. You know the simple way of figuring out how many d electrons it has? Is this numbering here. So if I go to cobalt plus 1, plus 2, plus 3 should be isoelectronic here. It's D6. Cobalt plus 2, D7. I just asked you what chromium plus 2 is. Chromium plus 2 is 1, 2 is D4. Chromium plus 3, 1, 2, 3 is D3. This is what we're going to do when we get to, because when we get to the second half, or the second part of chapter 24, we have to be able to get the d electrons right away. How many d electrons are there? Even though the d electrons don't participate in the bonding, the d electrons participate in the optical properties and the magnetic properties of these complexes. So we need to know how many d's there are. And so, but on the other hand, I'm calling the D's the core because they aren't going to participate in any kind of bonding in these complexes. But these D electrons participate in redox reactions. And so if you're looking in terms of redox, then I guess you could call those valence, because an oxidizer can come, as long as it's strong enough, and continue to pluck electrons off, until cobalt resists too much. In other words, the positive charge density on cobalt grows too high, and it becomes too difficult to oxidize. And so chromium is argon 3d6. I mean, cobalt is. Cobalt, the metal, is argon 4s2. What is it? 4s2 3d7. And so if you wanted to write the Lewis, I want to write this Lewis symbol for cobalt. Should I write 9 dots? 2, 4, 6, 8. I overdid it. Should I write 9 dots? It has 9 valence electrons, so I need to write 9 dots. And I think cobalt might be capable of forming 18 bonds, if we share one of those. Maybe we can't because, well, it's got an odd number of electrons, so surely it must be able to form 1 bond and have 4 lone pairs. Is that good? And so, yeah, you know what? Those D's really don't participate. And this is tricky because on the one hand, yes, valence. On the other hand, no. Because what happens is, if you look at cobalt technically has 2 valence electrons. And so if cobalt has 2 valence electrons and lost those 2, then the only ion we should be able to form is cobalt 2 plus. But it turns out that these D's aren't so stable. If we have D10, then you got a filled sublevel. D10 filled sublevel is hard to break. We see that in silver. For sure, silver is not going to react. If we look at silver, it will be krypton now, and it's going to be krypton 5s1 4d10. Silver is an exception as well because all we have to do is promote one of the s, and then we could fill the d. Okay, having a D sublevel that's filled is stable. And so what this means is this behaves as if it only has one valence electron because it's too hard to pluck another electron out of a filled D sublevel. But, and so there's only one charge for silver. The one charge is silver plus, so we don't have to worry about multiple charges for silver. And therefore, we don't use Roman numerals for silver. Silver is just always going to be +1. But for cobalt, it could be multiple. We could have cobalt +2. We take those 2 valence electrons. But, you know, if we have a powerful enough oxidizer can come in and pluck one of these, you know, these inner shell electrons, and form cobalt +3. Cobalt 3+ is quite reactive. But we see 3+. How about 4+? Do you see very many 4+ cations of the transition metals?
Iron?
Iron 4+, is that common? No. As a free ion. You see lead 4, but you never see it lead 4+. You always see it lead 4 as a compound, like PbO2. You need something to stabilize that. And so, yeah, the oxidation state here is +4. But you know, there's a lot of covalent interaction in this compound. It isn't totally ionic. And so, in a sense, you know, I can understand why some people prefer to call this a valence because it's susceptible to attack by an oxidizer. But the reason I don't call it valence is because people will start to try to draw more dots around this. And we don't want to. We don't want to draw any dots because whenever we have a transition metal ion, the first electrons to go are the valence. And then the rest are the inner shell electrons, which aren't even going to participate in the bonding. The bonding in these complexes, when an ammonia base comes here and attacks this, you know, we use MO theory to figure out the bonding. In fact, valence bond theory fails miserably for these complexes. You know, one part of valence bond theory is VSEPR, right? VSEPR stands for what? Valence shell, yeah. Yeah, something like that. Well, you don't have to know what the acronym stands for. You just got to know how to use it. And so let's use it here. What does valence shell electron pair repulsion tell you? Huh? What information do you get from VSEPR?
So the atom try to like pull apart each other.
What you get from VSEPR is the shape of the molecule. We want to know the shape of it. And so VSEPR, you know, if you have 3 groups, it's trigonal planar. If you have 4 groups, it's tetrahedral. And then you can get the hybridization, you know. And so, for example, using VSEPR in valence bond theory, we'd say this is tetrahedral, and the platinum must be sp3 hybridized, right? Because we don't have any lone pairs, and we just have all bonds, 4 bonds. And so this should be tetrahedral in shape. I didn't draw it like that, but that's what we predict. But, you know, this is not tetrahedral in shape. Do you know what the shape is? Of this. The shape of this is square planar. Now, why would the shape of this be square planar? You know, what's holding these flat? No, there are no 2 lone pairs. If there was a lone pair on top and a lone pair on bottom, sure, I'd go with you. But there isn't. You know, because bonding occurs in the valence shell. You know, bonding doesn't occur in the inner shells. And so here, what's happening is this. all that stuff that you learned in valence bond theory works well for organics, but it doesn't work well for O2. It doesn't work well for transition metal complexes. For transition metal complexes, we have to apply the full MO theory to get it. And so that brings up the question, then why is valence bond theory still taught, you know, if it doesn't work? MO theory works all the time, you know? And so why do they still teach it? And it's like this. One of the reasons that this question might come up is Bohr theory. Do you recall Bohr theory? You know, it doesn't matter. All you have to know is Bohr theory is invalid, right? It's no longer accepted. It's been abandoned, Bohr theory. We don't care about it that much. In fact, I respect Bohr because he came out with some great ideas, and I think that's why it's taught, you know, the whole thing. And it's also taught to show the scientific method because theories can evolve. But as for a reason for teaching it, I don't know. That's why I didn't spend much time on Bohr theory. But I did spend a lot of time on valence bond theory in Chem 1A. Bohr theory was abandoned. You never use it, Bohr theory, do you? No, pretty much. I mean, electrons do not orbit the nucleus. We don't use Bohr theory. But we continue to use valence bond theory, and so the question comes out, why wasn't valence bond theory abandoned like Bohr? It wouldn't hurt, you know, I don't know whose feelings would be hurt in particular, but in science they don't really care about feelings. And so why wasn't valence bond theory abandoned? I mean, it fails for these complexes. It fails for O2. Yeah, because it works. I mean, if you know the limitations of valence bond, it's okay to apply it because you get some reasonable picture of what's happening. But if you want something more accurate, you'd have to use MO, and then you have to know valence bond theory just doesn't work here. You know, what orbitals are we overlapping? Well, we could have an sp3 on chlorine overlapping with what orbital on platinum? Well, it turns out, yeah, platinum has some empty orbitals that are mixed with the orbitals on chlorine and forms these MOs. That's what's happening. And we aren't going to get into detail there other than just say that. And so this is why I say, you know, when I was talking about the fourth method of counting, the fourth method of counting was to try to get you in a different frame of mind because you can't apply the things that a lot of the things that you're used to applying in these complexes. Because they're a little different the way we treat them. Because we have to do a full MO treatment of these. And a full MO treatment, you know, how comfortable are you with MO theory? Not very, right? Because you didn't have much practice with it, and a lot of it's computational, you know, on the computer. Anyway, this is in square planar. In square planar, in chemistry, we're always interested in properties. Did I write this yesterday? Well, what is going to give you insight into the property of something like this? Well, one, the composition. But not only the composition, we need to know how things are structured. Exactly. And so composition of diamond, what is it? What's the composition of diamond? Carbon. What's the composition of graphite? Carbon. And so you have dramatically different properties based on just because they're structured differently. And so we're always trying to think in terms of composition and structure. So whenever we're given a composition, the composition is the formula. We want to know what the formula is. We want to know what the composition is because based on that, we can try to extract information to tell us some of the properties of that. Or sometimes we have an unknown. If we have an unknown, if we can measure some of the properties, then we'll get insight into the composition and structure of that unknown. Well, here we have this known composition, known structure. What are some of the properties? It turns out that this is a powerful chemotherapy agent. And chemotherapy agents are chemicals that are used in the treatment of, cancers, different types of cancers. This one's called cisplatin. And what is interesting about this is, having the two chlorines on the same side is critical, because if they had something called transplatin with the chlorines on opposite side, it isn't a powerful chemotherapy agent. Only cisplatin is. And it turns out that, because of the way the electronic environment is around this molecule is like a pancake, and what happens is it binds into a groove in the DNA and kind of gets stuck there. It prevents, DNA or whatever, replication. And so, continuing on with that, does this answer your question about the okay. Now, for valence electrons, you could argue with me. I don't mind that. You could say, well, I don't agree with you. I want to include the d electrons. That's fine. You could include the d electrons, and I would agree with that, because the d electrons also can react. And so, there could be more than one answer. Just like what a strong electrolyte is, there could be more than one answer for that. All right, let's take a look at composition and structure. Actually, are there any other questions before I move on? All right, let's take a look at composition and structure. Now, we have the amines and the amine. Or maybe I got that backwards. The amine or the amines. You know the difference? Yeah. Right. And so if I'm dealing with two M's here, then I'm dealing with ammonia. If I'm dealing with one M here, then I'm dealing with what we call an ammonia analog, something that behaves very similar to ammonia. The reason it behaves very similar to ammonia is because the nitrogen has the same electronic environment, or close to the same electronic environment as the nitrogen in ammonia. And so how can we get that? Well, what we have to do is we have to replace the hydrogen with something that's comparable. Now, what's comparable to hydrogen in terms of, let's say, in terms of electronegativity? Comparable to hydrogen in terms of electronegativity. Would you say lithium? It's in the same family. Or maybe it's fluorine. In fact, why does hydrogen occur in two different families?
Same property.
Yeah, it has similar properties to the group 1 and the group 17. And so actually its electronegativity is between boron and carbon. It's like midway in the periodic table. And so if I'm looking for something that has comparable electronegativity, then boron would be one. And so if I take out one of the hydrogens here and bond a boron, then that's not going to change, because I'm looking at, these amines are organic bases. Based on, actually I shouldn't say bases based, I'll say bases similar to ammonia. They're ammonia analogs, structural analogs, because they're very comparable. And why they're comparable is because what makes a good base, a good base? Yeah, you want something that's electron rich, because a good Lewis base should be able to donate a pair of electrons. Here. And when something donates a pair of electrons, it loses some of that negative charge density. And so let's do an aside here. Quick. Let me show you something like this. Do you remember this structure? Boron trifluoride? Boron trifluoride, there's something wrong with this Lewis structure. And so if I look at it, well, I want to first analyze it. So there are different ways you can analyze it. One, you can look at the formal charges. What are all the formal charges? 0. Well, that's okay. That's what you want for neutral molecules. When you look at the oxidation states, what are the oxidation states? Can you just read it off for fluorine? What is it? If there's a tug of war between fluorine and boron, who's going to win? Why? Why would fluorine win?
It's more ion, or more electronegative.
More electronegative. So fluorine wins, and that leaves fluorine with how many electrons? Well, 2, 4, 6, 8. It's supposed to have 7, so it's I got an extra electron. We say -1. Extra electron. And so all the fluorines are the same. They're all -1. And that leaves boron with no electrons. Boron should have 3 electrons, so this is going to be +3. So this is oxidation states. Well, that looks okay. And then the third method of counting electrons is the octet. And does the octet look good? Yeah, but you know, why does there need to be an exception? Because I can fix this readily. Do you know how I can fix this? I just create a double bond. And so I'll just have fluorine donate some of its electron density to boron. And when I have fluorine donate some of its electron density to boron, then I'll just form a double bond here. I'm sorry, what was that? There, now I have an octet. Everything has an octet. This is perfect, right?
Isn't boron can have more than 6 electrons around it?
Boron can have more than 6 electrons around it. Boron, you know, boron can have more than 6 electrons because, you know, if I only have 6 electrons in the valence shell, then I just bring it up to here. There's 2 more. There's room for 2 more, and then that would fill up the valence shell, the full valence shell. When we have a full valence shell, that would increase the stability of that. It's not because of that. What about this? Does that look good? In fact, we get resonance stabilization here because we could draw how many resonance forms for this? 3. And that will help stabilize it. And the bonds, we're going to get even stronger bonds because the bond order up here is what? The bond order. Not 3. Bond order is for an individual bond. 1. Bond order 1, bond order 1, bond order 1. What's the bond order here? Because if I look at the resonance hybrid, you guys remember the resonance hybrid? Yeah. What's the bond order in the resonance hybrid? 1 1/3. Is that right? Yeah. 1 1/3. And so a bond order of 1 1/3 is a stronger, more stable bond. So it seems like this is the way to go. But you know, whatever theory we have, that theory must agree with experimental fact.
How do you find the bond order again?
Oh, the bond order is simple. Single bond is bond order 1, double bond is bond order 2, triple bond is bond order 3. When we do the resonance hybrid here, what we do is we average it because in the hybrid, the pi electrons here are distributed over 3. And so what that means is that I have a total of 2, 4, 6, 8 electrons over 3 bonds. 8 electrons over 3 bonds evenly distributed is 8/3. 8/3 is, actually not 8/3. What is it? No, I should say, rather than electrons, because I'd have to divide it by 2. I'll just say bonds.
It was
6
each.
thirds, 1 1/3.
Well, I have 4 bonds, right? There were 4 bonds there distributed over 3 positions. So 4/3 bond each, 1 1/3 bond each. That's where it comes from. But you know, you don't have to worry about that just yet. We'll have more time to go through that. And so it seems that this might be good, except for one problem. Let's just look at one of the Lewis structures. Let me write this one up again. The problem has to do with formal charge. And so looking at the formal charges, what are the formal charges here? So this fluorine, actually the formal, actually I screwed this one up. Lone pair. This fluorine's formal charge is 0, 0, negative 1? No.
Oh yeah, plus 1.
Plus 1.
Boron is 1, negative.
Yeah, boron's negative. For formal charges, we don't write the 1. We just write the plus for plus 1 and minus for minus 1. And so these would be the formal charge. And so essentially, you've heard the rule. The rule is fluorine never forms more than 1 bond. If fluorine forms more than 1 bond, it'd have to lose too much electron density, which fluorine isn't going to be happy with. Because think about this: if there's a tie between, a tug of war between boron and fluorine, who's going to win? Fluorine. Fluorine is much more powerful than boron. So how can boron take an electron from fluorine? It can't. And so this is why we have the exception to the octet rule. The octet rule here is not going to be obeyed because fluorine is unwilling to give electron density to boron. It's too electronegative for that.
So the structure of the double bond with fluorine would be a better structure because I have a higher bond order.
Yeah, it has a high. There's so many arguments for going this route, except for one, a critical one, and that is right. Boron can't take the electron from fluorine. That's basically it. Well, that's for fluorine. Actually, let me erase this one here. Leave that one out. And so we have a violation of the octet rule here, but did I do carbon monoxide the other day? No? All right, what's the Lewis structure for carbon monoxide? I'll just draw it out. This is the Lewis structure for carbon monoxide, but carbon monoxide is weird because, well, it's not weird because it has an octet. It's weird because of not the triple bond. Yeah, the lone pair on carbon, and also the formal charge on carbon and oxygen. What are the formal charges here? -1 for carbon, +1 for oxygen. It's a neutral molecule. So -1 for carbon, plus for oxygen. And so that's weird. Why is this weird? Because if there's a tug of war between, yeah, who should win? Oxygen. But it's just the opposite. Carbon won. And so is there something wrong? There must be something wrong with the structure. But it turns out there's nothing wrong with the structure. This is the correct Lewis structure for this. And so in this case, we had a conflict. Over here we had a conflict. Is it better to have the octet, or is it better to have the formal charge stabilized? Over here it was better to have the formal charge stabilized because this formal charge arrangement was too unstable. And then we go over here. Is it better to have the octet, or is it better to have the formal charge stabilized? Over here, it's better to have the octet. And and we'll have to live with the formal charge like this.
Because you can't do anything.
Can't do anything about it unless, I mean, if you don't, if you want an octet, you can't do anything about it. You're right. There's nothing. And so sometimes we have conflicting information. And so this is why, this is why if you think off into the future, how can a computer replace somebody who can think and analyze this, right? I guess maybe a sophisticated computer programmer can come up with all these different paths, but do you see computers replacing people and analyzing this? Well, maybe. Hopefully not, unless there's better, obviously, things. But this also brings up the reason why, the computers are good at number crunching, but it's the interpretation of the numbers that's difficult. So even if a computer spits out a bunch of numbers, who's going to read those numbers, right? Who's going to analyze those numbers? And so this is the part. And so this is why we need some kind of points of reference. And we're going to base this. Well, experimental fact says this. And so now I have two donors. Look at this oxygen is a lone pair donor. This carbon is a lone pair donor. So if I had, let's say I had iron 2. Iron 2 in hemoglobin. Iron 2 in hemoglobin is bonded to 5 other atoms. And then there's one empty spot here. And so let's have a competition. We're going to have a competition between O2 and carbon monoxide. And we're looking at the heme part of hemoglobin. Which one do you think will win? Which one's a better base, do you think? Oxygen? We know oxygen binds to iron 2 in hemoglobin. Otherwise, respiration wouldn't take place.
O2.
And so, what do you think is a better base? O2? Yeah, O2 is naturally supposed to bind to blood. But let's look at it chemically. Well, O2 has 2 lone pairs. This only has 1 lone pair. Maybe this is better. But it's not just lone pair that we look at. What else do we look at? Well, the shape, the size, it's comparable in size.
The formal.
We look at the formal charge. This formal charge is 0. This formal charge is 0. What else could we look at? We could look at oxidation states. Now this is going to be kind of weird. But what are the oxidation states for carbon here? Oxygen? This oxygen?
Or no, it's -1. Or is it
0, 0.
I forgot the exception.
Actually, this is right.
I forgot the O2.
Oh, this one? Okay. 0, 0. 0, 0. Now, when I do this, oxidation states and formal charges, we're making opposite extreme assumptions. When I look at formal charge, I'm assuming that the bonding is 100% covalent. When I look at oxidation state, I'm assuming the bonding is 100% ionic. And so sometimes we have to use some judgment as far, because is this carbon electron rich or electron poor? What is it? Well, on the one hand, it says, wow, formal charge is saying it's electron rich. On the other hand, at the other extreme assumption, it's saying it's electron poor. So which is it? Is electron poor or electron rich? It's confusing, isn't it? Maybe. And so this is why you want to see lots of examples. You see lots and lots of examples, and then you can put perspective on things. And so it turns out, it depends on what we're doing. If we're looking at redox chemistry, or we're looking at acid-base properties. When we look at acid-base properties, the formal charges usually are the most important in considering acid-base. and then sometimes supplement those with oxidation states. But here, what do you think this bond is? Do you think this bond is more ionic, or do you think it's more covalent? It's more covalent. I mean, carbon and oxygen are right next to each other on the periodic table, so this would be, these purple ones should be more accurate than the red ones. And so does that mean, well, I should abandon the red ones because the red ones gave me the wrong data. In fact, experimental data says that the carbon has negative charge density on it from MO theory. And so should I abandon it? No, I don't abandon it because, whether it's formal charge or whether it's oxidation state, they're both extremely useful because we never, this was an unfair comparison. We never compare these two because the analogy is this would be comparing apples to oranges. And so I'm asking, which one is the biggest apple when you're looking at oranges, right? And so we can't. The only way we can compare the reds to each other, or we can compare the purples, but we cannot compare purples to red, and we shouldn't do that because we need to make sure that when we do a comparison, it's on a level playing field, right? And this is not. This is a totally different playing field. One's a baseball field, and the other's a soccer field. And so both are extremely useful in comparing with formal charges with formal charges on other species, oxidation states with oxidation states on other species. Because you make a complete 180 in terms of assumptions. All right, now looking at this, let's look at the formal charges here. Looking at the formal charges, which atom should be the most generous donor of electron density? Yeah, which one is the richest in terms of negative charge density and capable of donating? Is it this oxygen with 2 lone pairs? This oxygen with 1 lone pair, or this carbon with 1 lone pair? Which one do you think? Well, this oxygen with 2 lone pairs has a 0 formal charge, whereas this carbon has a negative, and so the carbon's kind of rich. It has 1 extra electron. And so we say that this one is going to be the most basic out of all 3 of these.
So we look at the oxidation state?
Well, we flip. And this is why we're going to get more practice doing this, because you got to get a feel for how to apply oxidation states and how to apply formal charges. And so we'll look at more molecules and stuff so you can understand that. But for right now, just pay attention to the formal charges. When we look at the formal charge, this one. And so in other words, if you're a positive 2 iron, this one's going to be the most attractive base. Or if you're a negative carbon atom, this is going to be the most attractive acid. And so this attacks this and binds. And so we end up with, we end up with carbon monoxide bound to iron and hemoglobin. And so we have that funny way of counting electrons. Here, remember what we just did with boron? This is okay because when fluorine donates electron density, it's going to change the formal charges on both of these. And so the fluorine goes up from negative to these aren't formal charges, those are. It goes up from 0 to positive 1, up in positive charge, and boron goes up in negative charge here. Over here, we expect carbon's giving electron density to iron, so shouldn't the iron 2 charge go from 2 plus to 1 plus? You see? But we count it differently. This is the 4th way of counting. We leave iron as iron 2, and we leave carbon monoxide as 0. All right. Versus oxygen. And so what turns out is, it turns out that carbon monoxide is a powerful Lewis base.
More powerful?
Much more powerful than oxygen. Oxygen is a very weak Lewis base. And that's good because what happens is when carbon monoxide binds to iron too, it doesn't let go. But when you look at transport of oxygen, the oxygen needs to let go. Otherwise, cell respiration can take place. And so here, when oxygen binds, it binds weakly. And that is, it's not a very strong bond and it's easy to break off. When carbon monoxide binds, it's a very strong bond. It's so strong that if an oxygen comes along here, it can't bind. There's no room for it. And so pretty much carbon monoxide will disable the heme group. And so strong base. What about this? Cyanide? Looks like this. We look at cyanide. Cyanide's an ion, so there's going to be a net charge. Now, is the negative charge on nitrogen or is the negative charge on carbon? We expect it to be on nitrogen because nitrogen is more electronegative. But the negative charge on cyanide is on, take a look at the formal charges. It's on carbon. And so what atom binds to hemoglobin in blood? Is it the carbon atom in cyanide or the nitrogen? The carbon. So carbon comes over here and binds. It binds so tightly that oxygen can't bind. And therefore, potentially you could die from asphyxiation, from carbon monoxide poisoning or cyanide poisoning. Now, what we want to do, and the tools we use aren't always the same because what we try to do is we try to analyze and extract as much information. And sometimes the information we extract is helpful. Sometimes it doesn't help us at all. And so what we'll do here is for the amines, we're going to try to figure out why certain amines are more basic than others. Sorry if I erased it too quick, but let's take a look at a simple amine where two of the hydrogens are left and we just replace one of the hydrogens with a carbon. What makes an amine basic or similar to ammonia is the electronegativity. The electronegativity of carbon versus hydrogen, the electronegativities aren't so different. And so what that means is that the hydrogen is going to have a certain pole opposing nitrogen, and carbon is going to have a certain pole. Well, nitrogen is stronger than both carbon and hydrogen, so nitrogen is going to end up getting the electron density. And so we get polarization of the electron cloud towards nitrogen. That leaves more negative charge buildup on nitrogen, less on carbon. So carbon is going to be delta plus, hydrogen is going to be delta plus, hydrogen this. And since they both have about the same strength, carbon and hydrogen, they're both going to be polarized in a similar fashion to ammonia. And so when we look at the electronic environment around, or the electron density around nitrogen in amines and ammonia, it looks the same. And so we make about the same delta minus here. But hydrogen isn't exactly the same as carbon. In fact, hydrogen has electronegativity 2.1. What's carbon's electronegativity? 2.5. And so when we think about carbon, carbon is actually a little stronger than hydrogen. And since it's a little stronger than hydrogen, what that means is it should suck in some more of the electron density here, pulling it away from nitrogen. And what that should do is it should shrink this delta minus just slightly. So if it shrinks the delta minus slightly, then which one is a better base? The more electron-rich ammonia or the less electron-rich amine? Yeah, so you expect ammonia should be a stronger base than a typical amine, where you replace the hydrogen with the carbon. But we have to be very careful with electronegativities because electronegativities change depending on the electron environment around the atom. And so I gave some examples yesterday. I think I gave some. You know, sometimes the classes get mixed up in my head. And so I have sodium plus, sodium. Did I give this one yesterday? You know, I always ask the question, if you need more, and most people want to get less sodium in their diet, but let's say you need more sodium in your diet. Which of these would you take? Sodium metal? No. You take sodium plus because we know that these two behave totally differently. And not only that, their electronegativities are going to be different. Tell me which of these three you expect to be the most electronegative. The one in the middle, this one? The electronegativity of sodium, I think, is 0.9. And so, well, these are all sodiums, right? And so all the electronegativities is 0.9. No. No, definitely not. And so, you know, this one in the middle is 0.9. And so is that the greatest electronegativity?
No.
No. The greatest electronegativity will be the one on the left. One on the left. So we know that electronegativity can depend on how the electronic environment surrounding the atom differs. And so let's look at the electronic environment around carbon. Well, the electronic environment around carbon depends on what it's bonded to. And so if I have, let's say I have methylamine. Methyl is CH3. And so this carbon has 3 hydrogens around it. Now let's take a look at the formal charge to analyze this. If we look at the formal charges, what are the formal charges in all the atoms here? They're all the same. The formal charges are all 0. And the formal charge really doesn't give us any useful information. But, you know, that's not our only tool. How about the octet rule? Does that help us? No. And so then we'll try oxidation state. Will oxidation state help us? And so let's calculate the oxidation states for the atoms in here. Let's see what they are. Carbon versus hydrogen. Carbon versus nitrogen. Carbon. And so we already did this one the other day, but what is the oxidation state on carbon? Not +1. -2. Why? Because it has 2, 4, 6, and it doesn't get any of these. So it has 6 electrons. It's supposed to have 4, so it's got 2 extra electrons, -2. Now, compare this carbon to the carbon in diamond. If we look at diamond, diamond just consists of sp3 carbon atoms. Forming a lattice, a network covalent lattice. And so if we look at diamond, what's the formal charge? Actually, I'm not dealing with formal charge. Remember, formal charges don't help us that much. And I don't want to calculate formal charge here and compare formal charge to oxidation state. That wouldn't be appropriate. And so I got to look at the oxidation state here and compare it. And so what's the oxidation state on carbon in diamond? Oxidation state is 0. So the question comes up, do these 2 carbon atoms have the same electronegativity? No. Which one has higher electronegativity? The carbon in diamond or the carbon in?
The other.
Higher electronegativity means, what does higher electronegativity mean? It means it has a stronger pull for electrons. So which one's going to pull harder for electrons in a tug of war? Diamond, right? Because this carbon already has 2 extra electrons, and so it's already kind of rich. And so this one has a weaker pull. In fact, since this one's electron rich, it's going to alter the electronic environment here, because now when we look at this, right, this one being electron rich, well, nitrogen wants electron density. And so nitrogen is going to pull here. And if it pulls, is carbon going to resist as strongly? No, because it's got extra electrons. It can afford to lose some electron density. And so if it loses some electron density, that means nitrogen is going to be even more electron rich. Does that make sense? And so when we looked at this earlier, we said that this should be a smaller delta minus than this. But that's with some generic carbon atom there. You know, we weren't looking at what it was bonded to and how that changes the electronegativity on carbon itself. And so when we look at this particular one, well, I see, wow, that's an electron-rich carbon. In fact, organic, you know, in organic chemistry, they would say this is kind of an electron pusher. You know, methyl, you know what ethyl is? Ethyl is CH3CH2, propyl. These hydrocarbon, what we call substituents here, are electron pushers. They're electron rich. They donate some electron density to this. If they donate electron density to this, then that means it's going to be even more negative than this. And so this is the reason why methylamine is a better base than ammonia. And you couldn't figure it out just by looking at the electronegativities off the chart, because those don't give you enough. Electronegativities vary depending on the environment here. And so let's try another example of this here.
So it's a better base because it's more electron rich?
I'm sorry?
It's a better base because it's more electron
Yeah.
rich?
Right. And so what do you think would happen if I went from methylamine to dimethylamine? If I put another methyl group on here, would that make it an even better base or a worse base? Yeah, and it would make it a better base. And so dimethylamine is better. What about trimethylamine? Even better. Okay. All right, now let's look at this molecule here. If we look at this molecule, this, even though it looks like an amine, this is not an amine. Why? You know, well, I look at it, nitrogen to hydrogen, nitrogen to hydrogen, nitrogen to carbon, it should be an amine. And so why isn't this one an amine and that one's amine? In fact, this one is not a good base. In fact, this is a better acid than a base. We'll talk about the acid properties maybe later. Why is that? Because if you just do electronegativity of carbon, 2.5, 2.5, then they're exactly the same thing. They wouldn't be any different, but we know we can't do that. Yeah, it's fluorine's fault, right. And what about fluorine makes this a very poor base? Right. This is an electron pusher. This is called an electron withdrawer. Why is this an electron withdrawer? Well, it's because of formal charge. Look at the formal charges. Do you see?
So before we were looking at oxidation states to show that that's a better base, but now we're looking at...
No, we're looking at formal charge just for the heck of it.
Oh,
It might not tell us anything. In fact, look at the formal charges and does it tell you anything? No. All the formal charges are zero like everything else. So formal charges don't tell us anything. Then we look at oxidation state. Let's look at the oxidation states. What are the oxidation states here?
Fluorine?
Yeah, fluorine. Fluorine versus carbon, who wins? Fluorine means -1. Here we don't write this minus, we call it -1 because oxidation states are different than formal charges. And those 3 fluorines are the same. Carbon versus nitrogen? Nitrogen. And so that means carbon's oxidation state will be
Plus 4.
plus 4 is correct. Plus 4. Now, what would you say, plus 4? Carbon plus 4, electron rich? Or electron poor? Electron poor means if there's electron density around, that carbon's going to want to take it. And that means it's going to be highly electronegative.
Like nitrogen is more.
Is nitrogen more electronegative?
It should be.
No, because that's not a fair comparison. What's the oxidation state on nitrogen here? The oxidation state on nitrogen here is 2, 4, 6, 8, minus 3, plus 1, plus 1. And so when you say nitrogen is more electronegative, you're comparing a neutral nitrogen atom with a neutral carbon atom. These are not neutral in this sense. And so really you're comparing nitrogen that's quite electron rich in this case. Well, just as a rough comparison, we'll talk more about electron rich. Nitrogen is happy as is, minus 3, but with something that's very poor. And so this changes the behavior, you know. This is like everybody started off kind of the same, but one person is dying of thirst and the other's got plenty of water, right? It's going to change their behavior because once the person who is dying of thirst might have been very sedate, you know. That's going to change. And so it's the same thing here. You know, once carbon was very weak, but when you take that many electrons from carbon, you think it's going to be happy. It's terribly, well, I shouldn't say terribly because these are relative terms. We got to compare it to something else. But, you know, when carbon gets plus 4, we'll use the periodic table to do this. Plus 1, plus 2, plus 3, plus 4 means it's lost all of its valence electrons. It's not going to be so happy, right? And nitrogen has extra electrons. And so what tends to happen is, this is electron withdrawer. It's going to pull the electron density. It's going to be a good fight, right? But now, for sure, carbon's going to pull a lot more density towards it. You know? So much so that what could happen is the carbon could end up being delta minus, and the nitrogen delta plus, just the opposite of what we think. But even if that doesn't happen, this delta minus is going to shrink, 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 right? And so as this delta minus shrinks, is that going to make it more basic or less basic? Less basic. In fact, this isn't a good base at all. This is why it's not an amine. This is more of an acid because of these hydrogens. Do you guys remember the term inductive effect? Inductive effect, have you heard? This is part of the inductive effect. The inductive effect is fluorine withdraws electron density, which impacts carbon, makes carbon withdraw electron density, and so on. It's a chain of events, you know, of how things impact each other in sequence. All right, so we're going to take more time to look at these, but you know, these base strengths are always complicated by the fact that we also have to look at how the orbitals do their LCAO. And so this is just the start. We're going to spend a lot more time analyzing these, especially when we get to the later stuff. But for right now, I want to take a look at some complexes. and talk about some jargon used in dealing with complexes. So let's take a look at some complexes here. Would you consider these nitrogens amine, like nitrogens? No? Yeah. Yeah? Well, we look at what it's bonded to, and organic chemists like to do this because sometimes the structures go quite big. And so what they like to do is just show the bonds, the carbon bonds. And so if there's no atom shown here, then that means there's a carbon atom there, and we've got a carbon-nitrogen single bond. This would be a carbon-carbon single bond. This is a carbon-carbon double bond, although they show this carbon. And so the atoms that are missing are carbon atoms. And sometimes they show the hydrogen, sometimes they don't. But what you do is you fill the valence. And so, for example, carbon likes to form 4, so we got a double, a single. That means there's got to be another bond here. This could be a hydrogen. And so this is just one molecule here. And this one molecule has how many amine groups? 4. And so, like polyprotic acids, we could have polybasic bases. A polybasic base would be something like this. This would be tetrabasic because it has 4 amines per molecule. Well, you know, those 4 amines here, the lone pairs aren't shown, and there's a bond here, so we got to displace those 2 hydrogens. Those are potential lone pair donors. So if we have a Lewis acid come along, we can bind to it. Now, if we look at these bonds, what kind of bonds are these? Those are single bonds, and they're also called these aren't ionic bonds. Remember when a Lewis acid reacts with a Lewis base, we don't form ionic bonds. We form covalent bonds, and they're given a special name. They're called, not network covalent, they're called... Ligands. Well, I'll talk about ligands in a second, but they aren't called ligands either. They're called coordinate covalent bonds or dative bonds. And so once we form it, then we can drop that because a coordinate covalent bond just looks like a covalent bond. So these are covalent bonds here. Now, you know, we don't worry about Vesper or any of this is a flat molecule here. And so, you know, this is kind of interesting because the amines or the nitrogens here, and pretty soon I'm going to stop calling them amines because I'm going to call these nitrogen donors. And so in this molecule, this is a porphyrin structure. In this porphyrin structure, we have 4 nitrogen donors. These are going to act as base sites here, a site being just a specific atom in the structure that reacts here. And those attach to the magnesium here. And there's a special name for this. This is called polydentate. And this base is a polydentate base, and bases in complexes are given another name. Bases are also called ligands. And so we could call this a polydentate base or a polydentate ligand. And with a polydentate ligand, this would be tetradentate, because since we have 4 nitrogens, those 4 nitrogens are going to bite into magnesium, that is bond to it, and hold it there. And so we got a tetradentate. Now, polydentate ligands are also called chelating agents. And so this would be a chelating agent. And with chelating comes from claw, you know. And like a claw on a crab, once it bites into it, it's difficult for this to break free. Because in order for that magnesium to break free, let's say we break this bond here. The collision, that bond breaks, there's still 3 other bonds. Okay, so we break this first bond, then we go to break the second bond, and we break the second bond, but while we're breaking the second bond, the first bond reforms. This connects again. And so what we have to do in order to break this free is to break all 4 at the same time. And so how easy is that? Not so easy. And so this is why it's difficult to remove the cations, these Lewis acids from chelating agents, like this. Well, this is the structure of chlorophyll A on the right. And you see these R groups here? These R groups are just whatever substituent we attach to it, like this. This is one of the most intense chelating agents out there. This is a single, actually, previously it was a molecule. This is a single ion. And this single ion bites into whatever, this is cobalt in this case, but whatever metal cation we have, it bites into it in 6 places. And therefore it's called a hexadentate base or hexadentate ligand. And the name of this is EDTA. EDTA stands for ethylene diamine tetracetate. EDTA is very difficult to break off because, essentially you need to break 6 of them simultaneously. And it turns out you might not have to do that. I'll tell you why. But this is a stereoscopic image of EDTA, or not stereo. This is just showing 2 isomers. We'll come back to it later. This is the EDTA structure. Ethylene, F stands for 2 carbons, and ethylene is CH2CH2. You know what methylene is?
1.
Yeah, 1 carbon, it would just be CH2. Propylene? 3. So propylene would just have CH2CH2CH2, butylene, etc. And so this is ethylene, and then diamine. Do you see the 2 amines? Here and here, diamine. And then tetra, 4. And have you seen this? Are you familiar with COO minus? Acetate, right? So this is kind of like acetate. Acetate would be CH3COO minus, but we have to drop one of the hydrogens to bond it to the amine. And so this is tetraacetate. Now, if you look at this, are these 2 oxygens bonded to each other? Am I going to run out of time again?
Yeah.
How much time do I have? 2 minutes?
A minute.
3 minutes?
Minute and 15 seconds.
He's at like 22, 25.
Yeah, I was keeping track of the time and then I just overshot it. You want to have a short 1-minute quiz?
No. Is that attendance?
No.
Maybe that's extra clarity.
No, all right, tomorrow we'll have another quiz, a little bit longer, 7.5 minutes.
How many points are the next?
The next quiz,
7.5.
I will make it either 5 points or 7.5 points, we'll see.
5 points.
Maybe I'll make it 5 points. Okay, but let me finish with this since I have another minute to talk about this. Okay, are these 2 oxygens bonded to each other? No. And so the carbon has a double bond O and a single bond O. And so it looks like how many donors are there? How many potential electron pair donors? These 2 oxygens, that's nitrogen. And so altogether there are 10. Right? 2, 4, 6, 8, 10. And so shouldn't it be a decadentate ligand, not a hexadentate ligand? Well, it turns out these 2 oxygens are too close to each other to properly bond. And so only 1 out of the 2 oxygens will bind. And so it turns out to be 1, 2, 3, 4, 5, 6, a hexadentate ligand. Now, this is, just talk about this. This is sodium EDTA. EDTA is used in heavy metal poisoning as well as as a preservative, etc. And so in heavy metal poisoning, I mean, you could get lead in your blood. Right? And so EDTA is often used to extract the lead out of your blood because the lead will attack certain proteins. But rather than having it attack the protein, if the EDTA comes along and encapsulates it, then it's pretty much neutralized. It can't bind to the protein now. And then you can excrete the EDTA lead complex. But I guess now I'm officially out of time, so I'll talk about this next time.